Static friction is the friction of a body at rest between the body and the surface that it's resting on. Kinetic friction is the friction between a body at a uniform movement or a body in motion and the surface that it's moving upon. And these things are not the same. If you've ever moved anything heavy, you know that it takes a big push to get it going, but once it's going, it doesn't take as much force to keep it going. That's because static friction is, generally speaking, larger than kinetic friction. So what does that have to do with force? Well, it's pretty intuitive. But there's one thing we've left out. Here's my body, and I'm sitting here at rest. In other words, there's no forces acting on my body. I'm not pushing it or pulling it either way. That makes perfect sense when we're talking about a body on a number line, but we're not talking about the x-axis anymore. We're talking about the body sitting on some sort of surface. So we're going to have our body sitting on some, again, immovable object. It could be a tabletop, could be a road, doesn't matter. It's sitting on something. And our body has a mass. You know that if I just had a body sitting in space and I was to release it, what would happen? Well, it would fall. It would fall to the ground. It would fall to the ground because there's a force acting on it, and that force, of course, is gravity. Gravity is nothing more than the acceleration of a body due to the force of gravity pulling it towards the center of the earth. So a body sitting here, not moving, must be held up by some force. And we're going to call that force N, which is what we call the normal force. If you're sitting in a chair right now, you can imagine there's a big N underneath your chair and a big arrow pointing up to the seat of the chair, and that's the force that's keeping you from falling into the center of the earth, the normal force. We're going to apply a force as before, and this could be from our spring or whatever, but a force that tends to want to pull our body in this direction. And since we now have friction, our body doesn't want to go. So we pull and we pull and we pull, and let's just say we start with a very little force, and then you pull and nothing happens because it's stuck to the ground with friction. And you pull a little bit more and pull a little bit more, and it never goes anywhere. Well, it never goes anywhere because it's being opposed by static friction. The force from friction will always equal the force that you're pulling up until the point where you overcome the friction and the thing begins to move. So when you're pulling just a little bit, you get a little reactive force from the friction. When you're pulling a little bit harder, you get more force due to the friction, and so on. When you pull it to the point where your force is greater than your friction, then our body starts moving. And now it's moving with a certain velocity, v, and this is kind of awkward, and we're pulling with a certain force, And that force is being resisted by now our kinetic friction, or sometimes people call it rolling friction in mechanics. If our force is greater than our kinetic friction, then our body is moving with an acceleration. If our force is just equal to kinetic friction, then we're going at a uniform velocity. Now these two forces, Fs and F sub k, are generally speaking proportional to this normal force. And you can think of this normal force as the weight of an object, because it is. Your normal force is equal to the mass of the object times the gravity, force of gravity, or I'm sorry, the acceleration of gravity. And if you remember our equation, force equals mass times acceleration, well, it's the same thing. This normal force is equal to the mass times acceleration due to gravity. So F of k is proportional to that normal force, same as F of s is proportional to the normal force. And again, that makes perfect sense. The heavier an object is, the harder it is to move. The constant of proportionality is something we call mu. It's the Greek letter mu. We use it for a variety of things, including prefix for micro, or 10 to the minus 6th. But here it's a constant of proportionality. So we can say that F of s equals mu sub s n, and that F of k equals mu sub k n. And these are things that have been measured and you can look up in a table. If you're sliding two pieces of steel on top of each other, for instance, you can look these up in a table and find out what the static friction is and what the kinetic friction is. And there's just one more concept I want to cover in this video. Obviously we live in a three-dimensional space. So far we've only been talking about single dimensions. Here I have my body B, and it's constrained so that it can only move in one dimension. What we have to remember is that velocity, acceleration, force, these are all vectors. And what a vector is just something that has direction. So if I'm pulling with a force F this way, it has a certain magnitude, it has a certain direction. I'm pulling with 20 pounds in this direction. If I turn around and pull from the other side, now I'm pulling with the same force, maybe 20 pounds, but I'm pulling in the other direction. And it's obvious, we call this F1 and F2, it's obvious that F1 equals minus F2. Even if the magnitude is the same, the direction is different. So just keep in the back of your mind that velocity, acceleration, and force, they not only have a magnitude, for instance, velocity 50 miles an hour, but they also have a direction. So it's 50 miles an hour south, for instance. Forces don't have to always act parallel to the motion that you're trying to analyze. For instance, I could be pulling up at an angle. or straight up, or straight down. And if I'm pulling it at an angle, or if I have velocity at an angle, or if I have acceleration at an angle, then what we need to be able to figure out is how much of that is in the direction of motion. And the way we do that is just simple geometry. We have an angle here, theta, and we know from geometry that if I make a right triangle here, that this side of the right triangle is equal to the hypotenuse times the cosine of the angle. So in this case here, I would say that F2 equals F3 times the cosine of the angle theta. And that's just a relationship to keep in your back pocket. It comes up from time to time. And again, it makes perfect sense. If theta equals 0, then F2 would be equal to F3 if this angle went to 0. And of course, cosine of 0 is 1, so that makes sense. F2 equals F3. If I was pulling straight up, if F3 was straight up and my angle was 90 degrees, cosine of 90 is 0. So in this case, F2 would be equal to 0 because all my force is going straight up. This block would not move left or right. It might move up, but it's not going to move left or right because all my force is going up. So just remember that. It's something that comes up over and over and over and over again. Now we've looked at position, changes in position with respect to time, which are velocity and acceleration. We've looked at the relationship between force and acceleration, that relationship being the mass of the object. Another word for mass equals inertia. Again, this is something that I think is pretty intuitive. The more inertia an object has, the more mass it has. Now the question is, where does the force come from? And we'll talk about that in the next video.